I've been talking about smooth manifolds several times in the last two lectures, but I've really given no examples at all except for the very elementary examples of spheres and disks. I'd like to start this lecture by giving a much less trivial example of a smooth manifold, which is very important in various parts of topology. The example is called a Grassmann manifold. And the intuitive idea behind the Grassmann manifold is the following. We take a fixed Euclidean space, say Rk, and look at all planes through the origin of a given dimension n. In other words, all n-dimensional subspaces. So I look at n planes through the origin in Rk. And there are various notations for this Grassmann manifold. The notation I like is Gn of Rk. Now, I'd said that this is a smooth manifold, so that, well, first of all, it's clear what this is a set. We know what it means to look at the set of all n planes through the origin in Rk. And it's more or less intuitive that there's a topology. That is, it makes sense to say that one plane is close to another, although it's a little work to define precisely how this topology is, to describe precisely how this topology is defined. But I want something more. I want it to be a smooth manifold. And with the definitions I've given the first time, there's only one way I can make something into a smooth manifold. I have to describe it as a subset of a Euclidean space. So what I want to do now is to describe a natural way of embedding this set in a certain high-dimensional Euclidean space. So let me start over again and think of this just as intuition. But I'll take as definition the following. Gn of Rk is the set of all k by k matrices. Now the set of which satisfy certain conditions. If I just said the set of all k by k matrices, I would have a Euclidean space of dimension k squared. So it's clear already that I've satisfied the condition that we have a subset of a Euclidean space. All k by k matrices such that, which are, and the first condition is symmetric. Let me write the matrix as A, so A is equal to A transpose. Second condition is idempotent. A is equal to A times A. And the third condition is that the trace of A should equal n. This is the first time the integer n has come into the definition. Well, this seems like a rather arbitrary definition at the moment, but let's look at that and see what it means. Each matrix we can think of as describing a linear transformation from the vector space Rk to itself. Now, if such a matrix is symmetric, it means geometrically that we can find an orthonormal basis for Ik consisting of eigenvectors of this linear transformation. So we can find a basis, orthonormal basis for Rk consisting of eigenvectors, that is, each of these vectors is carried into a multiple of itself by the corresponding linear transformation. And there'll be corresponding eigenvalues. Say lambda 1 up to lambda k. And now the condition that the transformation is idempotent tells us that each lambda will satisfy the equation lambda is equal to lambda times lambda. Now this lambda is a real number, so lambda must be either 0 or 1. So now we can see what we've got. We've got a linear transformation whose eigenvalues are all 0 and 1. The corresponding eigenvectors will, with eigenvalue 1, will give us one linear subspace, so that we can describe the situation as follows. We have a linear subspace spanned by the eigenvectors with eigenvalue 1, and then the remaining eigenvectors will span an orthogonal space. These will all have eigenvalue 0, and we can see what the linear transformation does. It leaves this plane fixed and collapses the orthogonal plane to a point. Now, what is the trace of such a transformation? It's clearly just the dimension of this plane. So here we have a plane of dimension n, and the orthogonal complement will have dimension k minus n. And we see that to each plane of dimension n through the origin, there's precisely one such transformation. And now, so I've defined a certain set in k-squared dimensional Euclidean space. One can prove that this is a smooth manifold. You can also here give a non-trivial, or, well, actually a fairly trivial example of a diffeomorphism between two differentiable manifolds. We take the differentiable manifold Gn of Rk and compare it with the differentiable manifold Gk minus n of Rk. I claim that we have a natural diffeomorphism between them. Namely, to each vector space V of dimension n in Rk, we associate the vector space V perpendicular of dimension k minus n. The correspondence from V to V perpendicular gives us a mapping from here to here. In terms of matrices, we map A to identity minus A. Well, this is the concept of a Grassmann manifold. And now let me give one important use of the Grassmann manifold. That is in defining what I will call the generalized Gauss map associated with a manifold. Gauss described the following construction. Suppose that one has a surface in 3 space. So we have 2 manifold in 3 space. And let me, over here, consider the unit sphere S2 in 3 space. So suppose that this is the origin of 3 space. And suppose that we have an orientation here. And to each point we have a unit normal vector, which can be, at each point there are actually 2 unit normal vectors in 2 directions, but given an orientation we can prefer one of them. And if I translate this vector to the origin, I get a point of the unit sphere. And the Gauss mapping is the mapping which assigns to each point of M the corresponding point of the unit sphere. And now I'd like to generalize this to case of I'll draw the same picture, but now I'll think of this as representing an n-dimensional manifold in k-dimensional space. And again, I'll draw the origin down here. And to each point, instead of looking at, well, one can look at the plane of normal vectors or the plane of tangent vectors. It doesn't matter, since, as we've seen, there's a given plane determines its orthogonal complement uniquely. So instead of looking at this normal direction, let's just look at the tangent direction. That is, to each point x, we associate the plane which best approximates x, translated so as to pass through the origin. By definition, this plane is called tangent space of n at x. And I want to think of this as a point in the Grassmann manifold. So in other words, I define generalized Gauss map G carrying M dimension n into the Grassmann manifold of n planes in K space, And I define this mapping by the formula g of x is equal to the matrix which corresponds to the orthogonal projection of Euclidean space Rk onto the tangent space of M at x. And clearly this, in the special case of a surface in 3 space, what we're mapping onto is the Grossman manifold of planes through the origin in 3 space. This is more familiarly known as the real projective space of dimension 2. It's closely related to the unit sphere. So in a sense which you can make precise, this is a generalization of Gauss's construction. And now let me give an illustration of the importance of this construction by mentioning the following problem. The problem is this: if we're given a manifold, we can ask whether or not it's a boundary. So suppose that we're given a manifold Mn in Rk, and let me make the following assumptions. Assume that M is smooth, compact, and let me assume that also that it's oriented. Perhaps I should describe, I've used this word orientation several times, but I haven't actually defined it yet. Let me quickly give a definition of what I mean by an oriented manifold. So this is an aside. Orientation. If we have a smooth manifold at point x, then we have the vector space tangent to M at x. And an orientation for M at the point is simply an orientation for this vector space. By definition, an orientation for a vector space is given by an ordered basis, say B1 up to Bn. And 2 bases for a vector space are said to define the same orientation if, when you express one basis in terms of the other, you get an n by n matrix with positive determinant. Another way of expressing it is if one can deform one basis continually into the other without ever introducing singularities, without ever introducing any linear relations between the basis vectors. So each vector space has precisely 2 orientations. Choose any ordered basis, it gives one orientation, and if we change the sign of one of the basis vectors, it reverses the orientation. And now for orientation of a manifold is an orientation of each of its tangent spaces. So this is a rather awkward object. It consists of orientations of infinitely many vector spaces, but these are required to be compatible in the sense that if you move from one point to another along a continuous curve, then the corresponding orientations vary continuously, in a sense which is not hard to make precise. So this is the definition of an orientation. And I consider a manifold which is smooth, compact, and oriented, and without boundary. And now the question is the following. Is Mn the boundary? Is it itself a boundary of a similar manifold of dimension n plus 1? So Wn plus 1, let me think of it as well as being embedded in Rk also, where Wn plus 1 should also be smooth and compact and oriented. This is a fundamental problem which gave rise to the subject known as cobordism theory. And there's a solution to this problem as follows. If we can, let me assume now that K is large. I think at least I'll need K to be at least 2n plus 1 or something of that order. It turns out that if K is sufficiently large, then it doesn't really matter what K is. The only important parameter here is n. There's a solution to this problem as follows. If we're given the manifold, we can consider the Gauss map from Mn to the Grossman manifold of n planes in K space. And here again, let me emphasize that K is large. And it turns out then that the essential properties of this space depend only on n. Well, I guess I'd better delete that statement. It would take too long to explain what I mean by it. The idea now is to look at homology theory. Remember that we have homology groups associated with Mn. We have homology groups associated with Gn of Rk. And we have a natural transformation induced by G called G star, which maps this additive group into this additive group. And perhaps I can explain one thing I mean is this. This group is independent of K, providing that we look at K definitely larger than I. This is one example of what I mean by saying that in this space we don't really care what K is, as long as K is large. Now, in the homology of any manifold, there's one particular class which is important, called the fundamental class of the manifold. Mn is compact, oriented, and without boundary. Boundary of M is vacuous. Then there's something which I'll write in this way. Bracket n, called the fundamental class, is an n-dimensional homology class. For those of you who are somewhat familiar with homology theory, if we cut the manifold up into little triangles, dimension or simplexes of dimension n, give each of them the orientation determined by the orientation of M, then if we add up all of these n-dimensional simplexes oriented in this way, we'll get an n-dimensional cycle, and this cycle determines the fundamental homology class of M. And now we can consider the image of this fundamental cycle under the Gauss map. So I'll take G star of M. And this is a homology class of dimension n in the Grossman manifold. If I assume that K is definitely bigger than n, then assume that K is definitely, I said bigger than n, bigger than 2n, then this group does not depend on K, and we have a homology class in a certain fixed group. This is a group, an additive group, depending only on n for K large. And these groups were first computed, I believe, by Pontryagin. And and they can be described quite explicitly. This group is a direct, of course it's an abelian group, and it turns out to be finitely generated, so it's a direct sum of cyclic groups, and in fact the cyclic groups are all either infinite cyclic, infinite cyclic group in this way, or they're cyclic of order 2. And for each dimension n, one can write down a quite explicit basis so that one has an element of an explicitly known group. And so to each manifold, one associates this invariant in an explicitly known group. And now the fundamental theorem of cobordism theory, of oriented cobordism theory, says that such manifold M is a boundary if and only if this invariant is 0. This is Mn is a boundary if and only if this invariant G starred of the fundamental cycle, this invariant lying in this explicitly known group, is 0. Or is usually expressed in a different way. One takes this invariant, and it's described by a certain number of integers coming from these infinite cyclic sum m's, and a certain number of integers modulo 2. These integers are called Pontryagin numbers of the manifold, and the integers modulo 2 are called Stiefel-Whitney numbers. So the more usual statement is that the manifold is a boundary if and only if all of its Pontryagin numbers and Stiefel-Whitney numbers are 0. This theorem is due to many people. Let me mention, well, Pontryagin and Thom and Wall. Well, so far I seem to have diverged completely from the subject matter I was talking about at the end of the last hour. I want to go back now and tie up this construction with the notion of tangent bundle, which I was describing then. More generally, let me consider the notion of a vector bundle. The concept of a vector bundle consists of the following. We have a pair of topological spaces and a mapping between them. This space D, the X is called the base space. Space E is called the total space. And let me call this mapping pi. And the fundamental property is the following. If we take the inverse image of a point in X, or if we take any X and X, and look at pi inverse of X, it's the set of all points in E which map into X, this should be a finite dimensional real vector space. So we think of E as a collection of many, many vector spaces, all lying next to each other. In terms of perhaps we can try to draw a picture like this. We think of this as E, and this is X down here, and the projection map pi. Then for each point here, we have a whole vector space. Particularly, will be a 0 element in this vector space. And these vector spaces all sit next to each other, so that as we move from one point to another in X, we get a continuous family of vector spaces. And as we move around X, we may get vector spaces moving around and coming them back to themselves in a non-trivial manner. A typical example is the Möbius band bundle. Which looks like the following. As the base space X, we take a circle. And as the total space E, we take a Möbius band, which I'm not very good at drawing. And I have to draw this as if these were, each segment here is a finite length. Actually, I'd like to think of it as a segment of infinite length, but that's a little hard to draw. So for each point x here, the inverse image will be one of these lines. And as we move around x, these lines go around and come back to themselves, but in the process they switch their orientation around. In here, to each point of x, one has a corresponding 0 vector, so one has a x itself sitting up here in the middle. This is an example of a vector bundle over the circle, where each fiber, each inverse image of a point, is a one-dimensional. Well, we can give, that's one example of a vector bundle. Another example is the one which we studied last time, the tangent bundle. Of a smooth manifold, Mn embedded in Rk. Here we define the total space, I'll call the total space of the tangent bundle T of M, is the set of pairs x, v, where x is a point of M and v is a point of Rk. But we don't consider arbitrary points of M cross Rk. If we did, we would just have a very trivial kind of vector bundle. What I want, rather, is pairs satisfying the special condition that v is tangent to M at x. And the projection map is defined by pi of xv equals x. So that the pi inverse of x, the set of all points which map into x under pi, can be simply identified with this tangent space. And here is another important example, namely the Grossman bundle. Here, the base space will be our Grossman manifold, which we think of intuitively as n planes through the origin in k space. And the total space, En of Rk, will be defined as follows. It's the set of all pairs A, V, where A is again a symmetric idempotent matrix with trace n, so A is an element of Gn of Rk, and V will be an element of Rk, and these are required to satisfy the following conditions, such that the condition I want is simply that V belongs to the linear space corresponding to A. In other words, V should be an eigenvalue with V should be an eigenvector corresponding to the eigenvalue 1, or in other words, I want the condition satisfied that A acting on the vector V is equal to V. And we define the projection map pi by pi of AV equals A. So corresponding to each point in the Grossman manifold, that is corresponding to each n plane through the origin, we have a vector space, the inverse image of this plane, and that vector space is exactly the n-dimensional vector space consisting of all vectors v which belong to that plane. And these two examples of vector bundles, the Grossman bundle and the tangent bundle, are related by the Gauss mapping. Namely, suppose we have the manifold Mn, and the Gauss mapping carrying it to Gn of Rk. Now over M one has the tangent manifold, and over the Grossman manifold one has the Grossman bundle. And now I claim there's a natural mapping here, which I'll call capital G. Capital G takes a point of the tangent space. Now remember that a point of T of M is a pair consisting of a point of the manifold and a tangent vector at that point. And I map this over to a point here. Now this has to consist of a point in the Grossman manifold, namely G of X, and a vector. So G of X we think of now intuitively as an n-plane through the origin, and the second half of this symbol has to be a vector in that plane. Well, I can take the vector V itself. And notice that if we go around this way, we go from point xv to g of x, small g of x. If we go around this way, we also go to small g of x. So that we have a commutative rectangle of mappings. And notice the following property also. Suppose we take any fiber here. So the fiber is a certain n-dimensional vector space. Corresponding to any point x, the inverse image is an n-dimensional vector space. That will map over here to a fiber, which is also an n-dimensional vector space. And each vector space here gets mapped precisely isomorphically onto the corresponding vector space here. So this diagram is an example of what's called a bundle map. Perhaps I should try to explain the general notion of a bundle map. We have one fiber bundle and a second fiber bundle. Then such a commutative diagram is called a bundle map if each fiber here gets mapped isomorphically onto the corresponding fiber here, isomorphically as a mapping of vector spaces. And now, it turns out that this mapping G, the knowledge of this mapping G is essentially completely equivalent to knowledge of the vector bundle. That is, one has the following classification theorem. Suppose we look at vector bundles, this type, where say X is a simplicial complex of dimension, say, M, and we have the fiber as a vector space of dimension N. And we tried to look at bundle mappings from this particular bundle to our bundle of to our Grossman manifold consisting of n planes, where n is this dimension, through the origin in a very large dimensional Euclidean space. Large means large with respect to n and m. Try to find such bundle mappings. It turns out they always exist and are always essentially unique. The Grossman bundle has the property that any bundle maps into it in a way which is unique up to homotopy. So that this mapping, which I'll again call G exists and is unique up to homotopy. So that for any vector bundle over such a complex X, there exists a corresponding Gauss map which describes the bundle. If we know the Gauss map, then it's possible to reconstruct the bundle. So instead of talking about vector bundles, we can instead just talk about mappings from X into this standard space, the Grossman manifold of n planes in a high-dimensional Euclidean space. And this shows that the problem of classifying vector bundles is completely equivalent to a problem in homotopy theory, the problem of classifying all homotopy classes of mappings from X, this standard universal model space. Now, I promised at the end of the last hour that I would try to describe something similar in my other categories. Now, I've been talking only about the differentiable category of smooth manifolds and smooth mappings. But suppose we try to look at the three categories simultaneously: the differentiable category, the piecewise linear category, or the topological category. So in each of these categories, we have a corresponding notion of manifold. There's smooth manifolds, piecewise linear manifolds, and topological manifolds. each of these cases, I'd like to define something like a tangent space or tangent bundle. Now, here the basic notion was of tangent vector, but clearly it's impossible to define the notion of a tangent vector at a point of a piecewise linear manifold or a topological manifold, so that we have to try something else. Well, one basic property of the defining property of the tangent plane is that it's a plane which looks most like the manifold at the point. We have a smooth manifold, and we look at its tangent plane at a point, then notice that a small neighborhood of the point in the tangent plane looks exactly like a small neighborhood of the point in the manifold, in the following very precise sense. We can take the orthogonal projection from M to the tangent plane of M at X, and some neighborhood of X will then go to a neighborhood of the origin, neighborhood of, call this projection pi, neighborhood of pi of X. And this mapping will be a diffeomorphism. In other words, here we have, let's say, an n-dimensional manifold. Here we have an n-dimensional plane, which is certainly also an n-dimensional manifold. And it's easy to check that this projection map is smooth, and its differential at the point X is non-singular. So by the inverse function theorem, we see that a small neighborhood maps diffeomorphically. So the basic idea I want to describe is this. Instead of using this notion of tangent plane, if we want to work just within the manifold itself, the best we can do is just to take the point X and to take a small neighborhood of X in the manifold itself. And this small neighborhood we'd like to think of as the fiber over the point X. Well, admittedly, this is a rather vague concept at the moment, but let's see what we can do with it. So in any one of these three categories, given a point X, we can look at some small neighborhood, say U sub X. Here we have a point X, and we can look at a small neighborhood U sub X. In the topological case, this still makes sense. Now, can we choose this neighborhood U sub X in some nice way? Well, one thing is obvious from the very definition of manifold in each of the categories. By definition, to say that something is a manifold means that locally it's isomorphic in the category to Euclidean space. So we can always choose U sub X to be isomorphic to an open set in Euclidean space. And I can say something a little sharper. There's the following obvious observation. Suppose I have an open set V in Euclidean space of dimension n. Then within this, I can choose a smaller open set, which is, say, a cube. And this small open cube is isomorphic, right? Use this symbol for isomorphism in the category, so this is to mean either diffeomorphism or piecewise linear homeomorphism or homeomorphism, depending on which of the three categories we're working in. This open cube is isomorphic to the entire space Rn. How do you see that? Well, let me write the open cube as the product of the interval from -1 to 1 with itself n times, to show that this product is isomorphic to the product of R with itself n times. It's clearly sufficient to consider the special case n equals 1. I have to show that an open interval from -1 to 1 is isomorphic with the whole real line. And to do that, we simply have to construct a function, say a function defined on the whole real line, and mapping it isomorphically onto the interval from -1 to 1. Well, in the piecewise linear case, one can construct such a function by, well, I have a little trouble drawing it. I just want to take line segments to construct a function which is strictly monotone and linear on each interval between consecutive integers, and maps the entire real line isomorphically onto the interval from -1 to 1. The differentiable case, we simply take a corresponding function. I think I need hyperbolic tangent, I believe, is such a function. But in any case, such functions are easy to construct. So what this argument shows is that each point on the manifold has a neighborhood which is isomorphic in the given category to the full Euclidean space of the same dimension. So we say, for each x in our manifold, there exists a neighborhood u sub x in the relative neighborhood, a neighborhood within the manifold M, which is isomorphic, either differentiably, piecewise linearly, or topologically isomorphic to the full Euclidean space of the same dimension. So as the first approximation, we can try the following. Let's try the following. We choose such a u sub x for each x. And now let's define the tangent space of M within the given category to be the set of pairs x, y in, well, now M cross M, such that y is in u sub x. And then we can define the projection map from Tm to M by pi of xy equals x. I'm trying to imitate the definition of tangent bundle in the differentiable case as closely as I can, and yet to give a definition which works simultaneously in each of these three categories. So if we make this definition, we certainly have a topological space, at least here, mapping down to M. And we certainly have the property that for each x, the inverse image of x, that's the set of all y belonging to u sub x, essentially. So the inverse image of each point will be isomorphic in the category to the full Euclidean space. So this may, at first glance, look like a satisfactory definition, but if you think a moment, you'll see that it couldn't possibly be satisfactory because we've simply had too many choices. For every single point of the manifold, we had to choose an arbitrary neighborhood. And there's no uniformity at all in this choice so far. The neighborhoods can vary in size in a completely wild manner. And this is not acceptable. What we have to do is impose a restriction that these neighborhoods, u sub x, will vary nicely with x in some sense. And one restriction that we can put on is the following. If we notice that from this definition, T of M is embedded in M cross M. We can draw a picture like this. Suppose I think of M as being the real line. And one point, the points of the diagonal are always in u sub x. If you notice that u sub x is the neighborhood of x. So x itself always belongs to u sub x, which means that the diagonal consisting of all points x, x is always in Tm. So in terms of a graph, I can draw the diagonal. For each point x, we have a corresponding neighborhood u sub x, which is represented in the picture by a little vertical line segment. So this construction for the special case of the real line means that for each point x, we've chosen a little vertical line segment. And so far, I haven't put any restriction on how these line segments are to vary with x. And now the condition that I want to put on is that T of M should be an open subset in M cross N. So it's an open neighborhood of the diagonal in M cross M. So that our picture will look like this. Well, here is M cross M, the diagonal. We want to take a neighborhood of this diagonal chosen in such a nice way that for each point x, the corresponding vertical slice here will be a neighborhood of X which is isomorphic to the full Euclidean space. And then there's a further condition one has to oppose, or at least I assume it's a further condition. I'm not quite sure that it doesn't follow, but I doubt if it does. That's the condition of local triviality. This is a condition which I slurred over in the case of a vector bundle also. It would have been essential there, but I didn't take time to give the condition. That's the condition this condition is the following. Each point of M has a neighborhood. Now I don't want to take the neighborhood use of X, but some unrelated neighborhood, say V, so that pi inverse V is in terms of the picture. If we have an open set V here, pi inverse V consists of everything which maps into it. Some sort of slice of our picture like this. Pi inverse V should be isomorphic to the product of V and Euclidean space. Because we know that for each point of V, the inverse image is a copy of Euclidean space, but we want these copies of Euclidean space to all fit together nicely so that the inverse image is isomorphic to the product, and this isomorphism should have special properties. That is, if we look at pi inverse V corresponding to V cross Rn, then we have pi mapping this down to V, and we have the obvious projection map to the first factor, which takes a pair xy to x. This should be commutative. So this projection, this isomorphism should make slices constant cross Rn correspond to fibers over here. This is the requirement of local triviality. So what I've done now may seem rather odd to you. I've tried to define something like a tangent bundle, but instead of defining something explicit, I've just defined a general class of constructions. I've said, to find the tangent bundle of M, you have to choose for each point of M a neighborhood, and you have to choose these neighborhoods so that they satisfy a number of very difficult-looking restrictions. Intuitively speaking, the neighborhood should vary continuously with X, and each neighborhood should be isomorphic to a full Euclidean space. And it's not at all obvious that these neighborhoods can be chosen in this way. And even if they can be chosen in this way, it's not at all obvious that the object one gets will really be an invariant of M. After all, you haven't defined T of M uniquely, you've just given an infinite number of possible choices of ways of constructing T of M, and there's no guarantee at all that any two of these will look alike. But it turns out, more or less miraculously, that this really does define something, since the T of M always can be chosen. It always is possible to choose these neighborhoods varying nicely with X, and the object one gets does not really depend on the particular choices. That is, if we have one choice of T of M and a second choice T prime of M, these are both fiber bundles over M, where the fiber is a Euclidean space, and it's always possible to choose an isomorphism from here to here, which carries each fiber isomorphically onto the corresponding fiber. This theorem is, well, it's really three different theorems depending on the three different categories. In the differentiable category, it is really not very difficult and doesn't give anything very new. It turns out that this notion of tangent bundle is more or less equivalent to the classical one. Tangent bundle in this sense determines the tangent bundle in the old sense and vice versa. But in the other two cases, it's something new, and the theorem that such tangent bundles can be constructed and are essentially unique is due to several people, to Keister, Maser, Kuiper. Keister gave the first proof in the topological case. I don't know, Maser or Kuiper gave the first proof in the piecewise linear case. So this gives us a notion of tangent bundle in any one of the three categories. And it turns out that one has a classification theory in each of these cases. So that in the differentiable case, you remember that a vector bundle over X determines and is determined by a mapping from X into the Grossman manifold. Say an n-dimensional vector bundle determines a mapping from X to the Grossman manifold of n planes in a large dimensional Euclidean space. Well, in each of the three categories, suppose I say in the category C, where C stands for either the differentiable, piecewise linear, or topological category, we can look at an n-dimensional, or simply an Rn bundle over X. It is a bundle consisting of where each fiber is a copy of the Euclidean space Rn. In each case, such bundles are classified by mappings of X into a universal example of such a bundle. The base space of that I'll call B sub C. So one has three different universal spaces. There's a classifying space for differentiable bundles, that's just our Grossman manifold. There's a classifying space for piecewise linear bundles, and there's a classifying space for topological bundles. I guess I should say B, C, comma, N, since it also depends on N. And these spaces sit in a natural order. That is, one has a mapping from the differentiable, which is more commonly known as the Grossman manifold, to the piecewise linear, and from there to the topological. And now, in terms of these mappings, we can try to answer questions such as the following. Suppose we're given, say, a piecewise linear manifold. Piecewise linear manifold. We can ask, does this piecewise linear manifold really come from a differentiable manifold? Is it possible to give this, it's a simplicial complex, is it possible to smooth it out in a nice way so as to get a differentiable manifold? Well, one gets an answer to that question as follows. The piecewise linear manifold has a tangent bundle, that is, and that determines a mapping into this classifying space for piecewise linear Euclidean space bundles. And now, if the manifold had a differentiable structure, there would be a mapping up into the Grossman manifold. And one can show that this diagram would be commutative. So one has a up to homotopy. So this gives us a reduction of this geometric problem to a problem in homotopy theory. Given this mapping, can it be lifted to a mapping up here so that this composition is homotopic to this mapping? And that's a problem which can be tackled by standard tools of homotopy theory. And similarly, one can suppose that one is given a topological manifold. And a topological manifold will determine a mapping into the top. One can try to lift it here or here. I'd like to state that the same theorem is true, that the manifold can be nicely triangulated if and only if it lifts to here. It can be given a differentiable structure if and only if it lifts to here. But that is a little too sharp a statement in the present state of our knowledge. These theorems are true in a certain stable sense. If you have a topological manifold, and if this mapping, say, can be lifted to here, then it is true that the manifold can be given a differentiable structure stably, in the sense that after you multiply it by some high-dimensional Euclidean space, then it can be smooth. But this given statement, which I tried to make, isn't known. But in any case, what this construction does is to give us three important examples of topological spaces whose homotopy theory is essential for the problem of understanding what topological manifolds are, what piecewise linear manifolds are, and what differentiable manifolds are. And there has been some progress in studying the homotopy theory of at least these two spaces, And lately, if reports one hears from Russia are true, the Soviet mathematician Novikov has made a very good start on determining the homotopy theory of this B topological. It's something which has been completely unknown up to the last month or so. But these are developments which still lie in the future, so I'd like to stop at this point.